plus 3. So it's 11:30. It's going to be 11:30 soon.
Okay. So then it's not so bad for you.
Oh, no, it's perfectly fine for me, actually. If you will ask me, then it's, I think, perfect. I mean,
Okay.
the conference will start from my time around 8:30 or so. And yeah.
Yeah, you just need to be little bit early.
Yeah. Hi, Jyotsna and Rashi.
Hello. Hello.
So, hello.
Professor Hem also. Hello, Professor Hem. How are you?
I'm fine. How are you?
I'm good. Thank
Nice
you.
to see you also again.
Yeah, I should be, right? Yeah.
So, we can check with our next speaker. Where? Yeah. Please.
Yeah, is this okay?
Yes.
Okay. Maybe you can like zoom out a bit. I think the full screen is not available.
I do that. Zoom out. Last time also I had the same problem with this.
Or maybe full screen option should be there.
No, here it is maybe.
View zoom out.
There is one fit page kind of. You can go to that option.
Fit page is there. I have.
Okay.
Oh.
If I put it in presentation mode, is this fine?
But maybe some text are covering.
Oh, sorry.
Is there an option for full screen mode?
Wait, I have to escape. View. There is an auto fit continuous view mode single page. No. Orientation.
No.
Rotate. Trim view. Trim margins.
No.
No.
And then I go to presentation. No.
Maybe you can try auto fit.
Auto fit doesn't give anything, right?
No, it doesn't.
Or zoom out.
No, or I think this is fine because I don't see that in.
Or you want the
in mode or something we don't see.
Presentation mode you don't see, is it?
No, presentation mode is there, but it's not working, right?
And sir, can you please check this fit width?
Oh, sorry.
Fit width.
There is fit width, yeah.
The third option.
Yeah.
Third option.
Fit width. Fit width is better, right?
Yes.
Okay.
Yes.
Fit width is better. Do I need to this thumbnail? That should be there, or it is visible? Okay, let it be there first.
Okay. Yeah. So let us start. So welcome everyone to the second session of the first day of this conference. I would like to invite Dr. Anup Kumar Singh from NISA Bhubaneswar to chair this session. Over to you, Dr. Anup.
Thank you, Rashi, for the introduction. And I would like to thank all the organizers for organizing this on the occasion of 60th birthday of Professor B. Ramakrishnan. And I don't know whether he is around or not. So I wish Ramkishar a very happy birthday first. And then the first speaker of this session is Professor C.S. Rajan from Tata Institute of Fundamental Research, Mumbai. And he will speak on finiteness theorem for potentially equivalent Galois representation. So before I invite Professor Rajan for this talk, I need his permission to record this lecture and live stream on YouTube.
Right. Yeah.
Okay, so thank you. So now I invite Professor Rajan to give his talk. Over to you, sir.
Yeah, so thank you, Anup, for the introduction, and I really thank the organizers for inviting me to give a talk on this occasion. So it's really it's a great pleasure to talk at this conference, and I've always been kind of admire and inspired by Ramki, especially when I see the way he has handled so many students, and all the students are so enthusiastic and energetic. And it's I don't know what is the secret with him. He has really, I would say, he's the Dronacharya of number theory in, or mathematics in India. I think the number of students he has kind of really brought up, and the tremendous enthusiasm. Of course, I had known him for a long time back when he had come over to attend some lectures.
Recording in progress.
And since then, I've got to know him, and it's always been a great pleasure to have known him and to have interacted with him. Thanks for all that. Okay, so let me talk. My talk is on finiteness theorems for potentially equivalent Galois representations. It's a joint work with Plavan Das, who was a student at Center for Excellence at Basic Sciences, but then for other reasons has now with the Center for Mathematics, the Chennai Mathematical Institute at Madras, CMI. So, okay. Okay. So we recall first the finiteness theorem of Faltings for pure Elliptic representations. So I'll just recall that. So what the finiteness criteria proved by Faltings is that given, so what you are given is a number field K, and you're given a number field K and a finite set of places S of K, right? And usually, of course, one assumes that S contains a set of Archimedean places, but that's doesn't missing. And you are given a natural number D. Okay, so you are looking at representations of the absolute Galois group. So then there exists a fixed finite set T of finite places of K. So T is a fixed finite set which depends only on the above data, the number field K, the set S, and D, and this is disjoint from S. So S is usually the set of ramified places for the representation which you are looking at. So that if you are given any continuous semi-simple representation rho from GK to GLD QL, so I'm looking at the Elliptic numbers, but more generally I can work with any non-Archimedean local field F of residue characteristic L and characteristic 0 that is unramified outside S. So these representations are unramified outside S. So I'm looking, so here GK is the absolute Galois group of K. So it's the Galois group of K bar over K. And I'm looking at D-dimensional representations. So then the finite set of traces of the Frobenius conjugacy classes. Since T consists of unramified places, at each such place, you have what is called a Frobenius conjugacy class. I don't think I'll go into the definition. But at the places belonging to T, it serves to uniquely determine the representation rho. So that means if you know that the character values at this finite, at the Frobenius conjugacy classes corresponding to the places at T, if you know them, then the representation is uniquely determined. Okay, so you just need to know the character values. So now what happens is, if you assume a purity hypothesis on the representations rho, so then you can deduce some finiteness results. So let me recall what is the notion of purity. So if you take an algebraic integer alpha, which is in Q bar, is said to be a Weyl number of weight W. So the weight is corresponding to either a finite field FQ or a non-Archimedean local field with finite residue field isomorphic to FQ. So if for any embedding, or you can so if you embed the ring of the field of algebraic numbers into complex numbers and take the usual absolute value, then it should be Q to the power W over 2, the absolute value. Or in other words, what we are saying is that alpha and all its conjugates have the same absolute value of which is Q to the power W over 2. So that is what it means to say it's Weyl number of weight W with respect to FQ or whatever it is with respect to Q. And you will say a representation rho from GK to GLD QL is said to be pure of weight W and degree at most D. So here I've made a slight difference, but anyway, it does not matter. That this small d and capital D can be different because I'm not assuming that the conjugacy classes are integral, but that's not a, in any practical sense, the conjugacy classes are integral. if at any unramified place V of K, the eigenvalues of the Frobenius conjugacy classes rho sigma V are algebraic integers of weight W and degree at most D over Q. Okay, so these are algebraic integers of weight W and degree at most D. So this is what one says is pure, that the eigenvalues of the Frobenius, all the conjugates have the same absolute value, which is Q to the power W over Q. Okay, so then what is the finiteness result? So, okay, first before that, the examples of pure representations, so they arise from the Galois representations attached to L-adic cohomology groups of smooth projective varieties defined over K. For in particular, if you take the Galois representations attached to the Tate modules of abelian varieties or elliptic curves defined over K, then, or if you are attaching it to holomorphic eigenforms, new forms, those are, these are representations which one knows to be pure. Okay, so the weight for an elliptic curve is 1, so you know that the eigenvalues of the Frobenius all absolute value p to the power half, or where if I'm working with an elliptic curve defined over Q. Yeah. Now, so the point, the corollary is that if you fix your K as K is a number field, you fix your S, the set of places where the thing can have ramification, you fix your degree D, or fixing an L and a W. Then what it says is then there are up to conjugation only finitely many continuous semi-simple Galois representations rho from the Galois group GK to GL and F. Sorry, I should have, yeah, that are unramified outside S and pure of degree at most D and weight W. Yeah, here of course I let N vary as long as this D and W are okay. So the corollary follows from the fact that there are only finitely many Weyl numbers attached to FQ of degree bounded by D and W, weight W. So once, see, the point is that if you have a Weyl number and all its conjugates are also algebraic integers, right? So then the polynomial or Z, you can look at its coefficients. The coefficients are all bounded because of the purity assumption. The coefficients are all, for instance, the first quotient, the leading quotient is not the leading quotient is 1, but it's an, and then you take the next one, which is the trace, and that is just some of the eigenvalues. So it is just bounded by some constant times Q to the power W over 2. And the various other quotients are bounded because of they are elementary symmetric polynomials in the conjugates of the Weyl number. So they are all bounded, and so there are only finitely many polynomials, and that tells you that there are only finitely many Weyl numbers attached to FQ of degree bounded by D and weight W. So from this corollary follows. So one of our aims out here is to generalize Faltings finiteness theorems given above to the context of potential equivalence. Okay, and in joint work with Vijay Patankar, we had considered refined versions of strong multiplicity 1 theorem, were considered for potentially equivalent L-adic representations of the absolute Galois group associated to number field K. And now I just want to say that two representations of a group are said to be potentially equivalent if they become isomorphic upon restricting to a subgroup of finite index. Okay. So I would say that now. So just let me go back and say this. So we are saying that two representations are equivalent if upon restricting to a subgroup of finite index they become equivalent. And what we want to do is to relate this to some character theory. So part of this work was done with Vijay Patankar, relating this to character theory, but we got to understand it better and put it in a more clearer manner with the work with Plummer. Yeah. So what we do, so you define, given a linear representation rho from gamma to GL and F, you define its M power character or M character or M trace as the trace of evaluated at an element. You look at the trace of rho of G to the power M for G in gamma. Okay. So two representations of gamma to GL and F are said to be M character equivalent if their M character functions coincide. Okay, so we have two definitions. One is potentially equivalent and another is M character. Okay. Oh, sorry. I just okay. I think I did a mistake. I should have this. Let me take a slight break. I just want to give an idea of proof of the Faltings theorem. What is the choice of this the set T? So let me just recall what is Faltings finiteness theorem. So yeah. So sorry. No, I just before that. Yeah. So there is this exists a fixed finite set T of finite places of K disjoint from the set S. So I would just like to know how do we get this set T, and that is what I'm going to indicate in this slide. Yeah. Yeah. So what happens is, so by so this is a choice of T I just want to indicate. By Hermite-Minkowski, there are only finitely many extensions of degree at most L to the power 2n squared, and that are sorry, I need to which are unramified outside S. Okay, so Hermite-Minkowski says that if you have fixed a number field and fixed a finite set of places S, and look at extensions which are unramified outside S and of bounded degree, then there are only finitely many. Right? So there are only finitely many such extensions. Now you let L be the compositum of all such extensions. L is a finite extension of K, and we let G be its Galois group. And by Chebotarev, there exists a finite set of places of K, such that which are unramified in L, such that which is disjoint from S, right? Such that the Frobenius conjugacy classes belonging to T cover the conjugacy classes in Galois group L over K. Look, the extension L over K is unramified outside S by whatever the choice. It's a finite extension, and so there are finitely many conjugacy classes in G, and we can by Chebotarev I can pick some finite set T, or which is disjoint from S and which covers the conjugacy classes in L over K. So then you apply to Nakayama's lemma to complete the proof. So yeah, so that is the idea of Faltings theorem, that it basically rests on Hermite-Minkowski, the finiteness theorem of Hermite-Minkowski for number fields. Okay, now we go back to, so as I said, our aim is to generalize some of this to the context of potential equals. Okay, so now I go back to what we already introduced, and I want to say that the equivalence between potential equivalence and character equivalence. So suppose gamma is an abstract group, and ρ1, ρ2 from gamma to GL and F are semi-simple representations of gamma, right? And where F is a field of characteristic 0. Then the following are equivalent. Okay, so one is that the representations ρ1 and ρ2 are potentially equivalent, and second is there exists some natural number M such that the M power characters are equal. Okay, that is chi ρ1 M is equal to chi ρ2 M. Okay. So what this is, of course, if M equal to 1, it is well known that the representations are equivalent if and only if the characters are equal, right? So this is in a sense generalizing it to potential equivalence. The proof is not very complicated, and but what happens is if you use a bit of algebraic group theory, it is easy. So what happens is, since characters are all algebraic and linear, so we can look at, one can work with algebraic closure of ρ1 cross ρ2 gamma inside GLN cross GLN, right? So our assumptions are that these representations ρ1 and ρ2 are semi-simple. So what happens is, this is a reductive group G, right? And which allows us to, so now we can replace gamma by G, and G sits inside GLN cross GLN, and you can consider ρ1 and ρ2 are the projections of G to GLN and cross GLN. So these are algebraic, it's a reductive group, and you have two representations. To the case that gamma equal to G is a reductive algebraic group. Okay. one then uses the fact that for a characteristic 0 algebraically closed field, the map x goes to x power m is surjective on the connected component. So if you have a connected reductive group or connected algebraic group in this thing, the connected component of the identity, then the nth power map is always surjective. And if you use this fact, then this above theorem is really okay. So that's proof that the character is equivalent. Knowing an equality of the m power character is equivalent to saying that the representations are potentially equivalent. Now, when you consider potential equivalence, you can consider a refinement of the concept, which is very natural, and that is to look at element-wise potentially equivalent. Okay, but with m depending on the element of the group. Okay, right. So but what I'm going to say is I'm not going to assume character values are equivalent, but only saying that the elements are going to be conjugate. So what you're said to be element-wise potentially equivalent if for any g in gamma there exists a natural number mg. So this mg depends on gamma such that the elements rho1 g to the power mg and rho2 g to the power mg are conjugate in GL and F. Yeah, so they have the same set of eigenvalues in some algebraic, right? So that is what one is saying. Of course, here I'm not assuming g, the element rho1 g is semi-simple, but anyway, that's not an issue. Yeah, so basically we are saying that they are conjugate. It's enough to assume only that the semi-simple part is conjugate, but it's okay. So using the fact that in any non-Archimedean field, local field f of characteristic 0, so if you take so now see the previous theorem was f is any field of characteristic 0, but now we restrict our attention to a non-Archimedean local field f of characteristic 0, and the fact is that what we are going to use is that there are only finitely many roots of unity in any non-Archimedean local field of characteristic 0. So using this fact, we can prove the following theorem, which is now I work with an abstract group, and again I take representations rho1, rho2 as before, semi-simple representations. But now f is a non-Archimedean local field of characteristic 0. Then the following are equal. The representations rho1 and rho2 are potentially equivalent. Yeah. And the representations rho1 and rho2 are element-wise potentially equivalent. Yeah, so that is what we have said. And there exists a natural number m depending only on n and f, so that the m power characters are equal. Right. We know that the equivalence of 1 and 2, 1 and 3. So what we have to show is, of course, 1 implies 2, 2 implies potentially equivalent, 2 implies. So what you have to say is that 2 implies 3. That is all that one needs to do, and that follows from because f is a local field or non-Archimedean local field of characteristic 0, so there are only finitely many roots of unity, and if it is element-wise potentially equivalent, then you can uniformly bound an M, which is independent of G. Okay, so that is a. Okay. But now I want to consider potential equivalence, but now in the context of Elliptic representation of the absolute Galois group of number fields, right? In which case, what we are going to do is we are going to work with Frobenius conjugacy classes. Right, so we need to kind of move to a slightly more this thing, and so for this, of course, what we need to do, what we use is Chebotarev type density results, which will allow us to work with Frobenius conjugacy classes in determining potential equivalence of representations. So, what are the Chebotarev type density results? The usual Chebotarev is when G is a finite group, and what we can do is that we can work, and then you're looking at a Galois group of a finite extension. But here I'm looking at Elliptic representation. So, and I would like to try to state a Chebotarev theorem for some conjugacy class. So this can be done if the conjugacy class is algebraically defined. So what happens is, so the conjugacy class is X. So I'm the conjugacy condition is a closed algebraic subvariety X of GLM, right? Which is also conjugation invariant by the image of rho GK. So I'm taking something which is invariant under the image of rho of GK, and so I'm looking at a closed subvariety. So this is So then what the algebraic Chebotarev density theorem, basically something due to Serre and this thing, says that gives the density of Frobenius conjugacy classes that lie in X, right? So I'm of course assuming the representation of rho is unramified outside S. So that is, so it again it's a finite, it's a rational number, it's not anything missing. It just counts the number of connected components of G that lie in X divided by the total number of connected components of G. But what is G out here? It is, of course, it's a Zariski closure, algebraic closure of the image of rho GK. So where G is a algebraic is what is called the algebraic monodromic rho of rho. This is algebraic closure of the image rho GK inside GL. Okay, so this is what one has, right? That so you look at the connected components of G phi of G which lie inside X and divide by the total number of connected components. So that is the density of conjugacy classes which whose conjugacy classes lie inside X. And of course, if G is a finite group, this is the usual Chebotarev density theorem. Okay, but for any algebraic group, as long as the conjugacy condition is algebraic, then this goes through. Okay, so using this theorem, we can prove this, and the theorem is as follows. So you are looking at continuous semisimple representations of GK to GL and QL. Then the following are equivalent. The representations ρ1 and ρ2 are potentially equivalent. There exists a set of places T of K of upper density. So here I'm looking at probability density. If I'm looking at limb soup, it's always defined. And so the limb soup is what is called upper density. Otherwise, it just counts the number of places in T divided by the total number of places up to X, and then that is the limb soup of it. The norm is bounded by X. So as you let X go to infinity. So that the local components, so given any place V, you can look at the local components, which is you can look at the local decomposition group at V. And so you can define the restriction or whatever which is well defined only up to conjugacy. That the local components ρ1V and ρ2V are potentially equivalent as representations of GK. That means, okay, so that is a local potential, locally equivalent. And there exists a positive integer m depending only on n and QL, such that at a set of places of upper density 1, which are unramified for ρ1 and ρ2, then trace of ρ1 of sigma v power m equal to trace of ρ2 of sigma v power m. And then what we are saying is that the representations ρ1 and ρ2 are m trace equivalent for some natural number m. So what we are saying is, in the context of the Elliptic representations of the absolute Galois group of a number field, you can work with potentially equivalent, locally potentially equivalent, right, at a set of places of density 1, and still you'll be able to say that the representations are m trace equivalent. So this is what the Chebotarev type theorems will allow you to say. Okay, I can work instead of QL, I can work with any non-Archimedean local field. That's not a problem. Okay, so now we come to extending Faltings criteria to the context of m power characters. So what is a theorem? That's a thing which we want to say. So we have K is a number field, and I fixed a rational number L, natural numbers N, A, and M, and S is a finite set of places and whatnot containing the places of L of K. So then, as usual, there exists a finite set T of finite places of K. So I'm given all this input, number field K, a rational prime L, or I can actually here I've made a slightly general situation. This A is 1 because of this thing, but anyway, and M is right, okay. Then there is a finite set of places with the following property. Let me just state what it is. Suppose ρ1, ρ2 are representations of GK to GL and F are two continuous semisimple representations, where F is a non-Archimedean local field with residue field of cardinality L to the power A, right? So the field F is allowed to vary, but the cardinality is fixed. The residue field cardinality is L power A. So you can take highly ramified extensions also. And you assume, what you have to assume apart from the original Faltings theorem is that the inertia at V it has to act by scalar matrices of order dividing M. Okay. So the M is that we want to say that the inertia acts by scalar matrices, and it should act by order dividing M, and that the representation should satisfy the following hypothesis. So see this, I should say that the sigma v power m, the rho 1 sigma v power m is well defined. It's not that rho 1 sigma v is defined only up to some root of unity, but rho 1 sigma v power m is well defined because this inertia is acting by scalar matrices of order dividing m. And so we ask for an equality of this characters. Okay, and so that is what we are saying. Rho 1 sigma v power m equal to rho 2 sigma v power m, right? And once that, then rho 1 and rho 2 are potentially isomorphic. So what the modification of Faltings theorem is that we are relaxing the condition that the representations are unramified outside S. However, we are imposing that the inertia acts somewhat mildly by scalar matrices of order dividing M. Okay, and then one can get this that the representations are. Then if you know that they are potentially equivalent, because that is the condition which will be defined, that rho 1 sigma v power m equal to trace of rho 2 sigma v power m, then rho 1 and rho 2 are potentially equivalent, because the inertias are well defined, the conjugacy class are well defined only up to taking some power of. Okay. So the proof of the above theorem, it basically follows the lines of Faltings theorem, but what we do is we use the linearization of the m power character chi power m using Newton identities. So Newton identities express the complete symmetric polynomial. You can express this chi m as an integral linear combination of, see, this chi m is really related to the complete symmetric polynomial in m variables, because not complete symmetric polynomial, the Newton polynomial, right? What is the value of chi m is chi of rho to the power m, the trace of rho to the power rho of sigma to the power m, so which is just the m sum of the mth power of the eigenvalues. Yes, sorry. Is there some question? So chi m, actually you can write it via Newton identities as an integral linear combination of characters which are exterior powers of rho, and that is the proof that is an integral. So that is a finite sum which you can write, and that is basically, that's, you use that and use this. Okay, so as I said, that so we have got a proof of we have extended Faltings theorem where we allow some ramification outside S, but the ramification is somewhat mild, that the inertia has to act by a character. Okay, scalar character, which is this. So combining with purity, we get the following consequences. So you fix some natural numbers n, w, and d, and then you are looking at k be a number field, and L is a rational prime. S is a finite set of non-Archimedean places of K containing, and F is whatever is the same. Then there are up to potential equivalents only finitely many continuous semisimple Galois representations rho from GK to GN and F. Okay, such that the inertia at places outside X acts by a scalar matrix and pure of degree at most D and weight W. Okay, because I have fixed F, then there are only finitely many roots of unity. So this order of the with which the inertia will act is bounded, right? And so this is a theorem that if you assume some purity, pure meaning is, again, the purity is the same. The eigenvalues of the Frobenius or Frobenius powers pure of whatever weight, and at most D and weight W. So this is what. Okay, so that's one can state this. Okay, so for example, what happens is one can work with this. So if I work in the context of abelian varieties or elliptic curves, if you fix of dimension G defined over K, and suppose such that the inertia at a place V not in S acts by scalars on a Tate module. So the inertia should act by scalars for L co-prime to the residue characteristic of this. So you have fixed some L, which is co-prime to the, we have fixed some L, and B is residue characteristic of B is co-prime to it. Right? So you are looking at some places and you want to say that it should act as scalars. Okay. Now I just want, I want to say what are the motivation for proving such above theorems. So I would, instead of giving the motivation at the beginning, I'm going to slowly come to why we are looking at those theorems. So we now you deduce an analog of Faltings finiteness theorem, or for what we call as twist unramified representations. And so we fix K, S, L, N, W, and D, and then up to twisting by finite order characters, chi from GK to H star. What you can say is that there are only finitely many isomorphs and classes of continuous semisimple representations, rho from GK to GLNF, satisfying the following. The representations rho are twist unramified outside S. That means by twisting by a finite order character, it's unramified. Of course, the twisting will depend on the place V. For every place V, you might have to twist by a different character. We are not saying it is uniformly twisted by a character, and that is part of the theorem, right? The conclusion of the theorem. And rho is pure of weight at most W and degree bounded by D. Okay, so that is, and what we need to assume is that the connected component G0 rho of identity of the algebraic monodromic group, which we are already talked about at the beginning, it acts absolutely irreducibly on Fn. Okay, so this connected component, it acts absolutely irreducibly on F bar n. On this representation, it is absolutely irreducible. So this is, for example, if you're working with non-CM elliptic curves, so then this works. So let's just work it out. So one of the motivating example from the work was this motivation for our work. So we have fixed a finite set containing the Archimedean primes of K. Then what Basis and Boxall did was to say that the set of isomorphs and classes of non-CM elliptic curves defined over K with twisted good reduction outside S is finite up to twist. Yeah, so if you look at the set of isomorphs and classes of non-CM elliptic curves defined over K, and the twist, of course, depends on the place outside S, but there are only finitely many which twist up to twist by a character. And the proof of Basis and Boxall was to use the method of Shafarevich, who used transcendental number theory, this work of Siegel on finiteness of integral solutions to the discriminant kind of equation, and so which is a cubic, and so but ours is purely Elliptic, it's algebraic proof, and of course as an advantage you can extend it to a billion varieties. So now I'm going to give a slightly different kind of results. So these are elliptic curves which with potentially good reduction in a quadratic extension. And so we want to apply what we have done to in this setting. So you look at, you fix a number field K containing the Archimedean primes of K, right? And then there are up to twists, only finitely many K isomorphs and classes of non-CM elliptic curves E defined over K. So I'm looking at elliptic curves E defined over K. I'm not saying anything about right now the ramification of E, but what I'm going to say right now is that such that for some quadratic extension L of K, the L can be different. It need not be the same. It can you can let it vary over all quadratic extensions. The elliptic curve E acquires good reduction outside the places of L lying above S. Okay. So what we are saying is up to twisting by characters, like what Dipendra had talked in the morning today when he was looking at the elliptic curves y squared equal to x cubed minus n squared x, which are all twists. Of course, they are all twists of the same elliptic curve. But what we are saying is that there are only finitely many up to twice of K isomorphism classes of non-CM elliptic curves E defined over K, so that they acquire good reduction in some quadratic extension. Right. So this is what you're saying. So see, some of these questions, of course, are kind of related to a work of Hida and rather related meaning, yeah, it looks and this work of Ribbett on what are called Q curves and Q varieties. But we have not really been able to get going on such questions because of some other issues. But so let me, yeah, I'm just saying this. The idea of the proof for this above theorem is we have to show that the inertia acts by a character. And because we are working with a quadratic extension, what we need to say is essentially that the eigenvalue 1 is not taken by inertia. So the inertia should not take the value plus minus 1, right? If it takes 1 and minus 1, this thing. So if it acts by only minus, if the inertia is non-trivial, then it has to be a scalar which is minus 1. It can't be the matrix 1, minus 1 or things like that. Some number of ones and some number of minus ones. So that is the thing which you have to say. And what happens is for the elliptic curves, one can use the theory of Néron models to show this. But this theorem above result can be also generalized to abelian varieties, which what we have to assume, which are totally ramified, what are called totally ramified reduction outside S. So, which means that it doesn't have an outside S. It does not. When you look at the reduction, it should not have an abelian variety component. It is only multiplicative or additive part, but which requires additive reduction, which has potentially good reduction in some quadratic extension, right? So this is what we need. Okay. This for the generalization to abelian varieties, one makes use of a theorem of Lenstra and Oort, who say that basically that the above property, that the eigenvalue 1 is not taken by inertia. So once you use the theorem, so that they use the monodromy pairing used by Grothendieck and other things, and to prove the theorem. And once you use the theorem that the eigenvalue 1 is not taken, then you know that the inertia has to act by a character, and then our theorem applies. So we do say that if you have abelian varieties which have good reduction in a quadratic extension outside the primes lying outside S, then we know there are only finitely many up to twist by S. So that is all that I have to say in today's talk. And so happy birthday, Ramki, and really best wishes for a long and productive life. And I hope you continue to inspire and many more students with the same kind of enthusiasm towards mathematics that you have. Yeah, all that. Thanks, Ramki, for it.
Thank you, sir, for this nice talk. So now, any questions or comments? So this floor will be open for some time for question answers.
Yeah, so I have a question.
Yeah.
Hello, sir. In one of the theorem, you have proved that if the m power characters are same for upper density 1, then they are potentially equivalent, right?
Right.
But in IMRN paper, you have already proved that for m equal to 1, if you assume that the Lagrange monodromic group of rho 1 is connected, then actually the assumption that m power character, I mean the 1 power character or just the trace character, is the equality of the trace character is sufficient for only upper density, a positive upper density of prime. Right. So do you think that the similar thing will happen for m power character?
No, it doesn't. What happens is that's a very so I should say that Patakar and myself wrongly had claimed this result, and then Sarah had pointed a counter example. The point is, I told you that we can reduce it to the case when for m equal to 1, what happens is we can work with the connected component. There is no x going to x power m, right? Yeah. But what you need is that the map x going to x power m in general, whether it kind of, there is some surjectivity property. But if I take, for instance, if I take the Galois group, say corresponding to a non-CM for a CM elliptic curve, right, which is a normalizer of a torus, right, and then the connected component, actually its square is its fourth power is going to be trivial. It will that is the non-connected component. If I take 0 x whatever, the non-connected component of identity is mth power, its fourth power is going to be trivial. This is a property of SL2 or whatever it is. It's there. So it fails. But so this requires some work, and yes, it can be repaired, but there are these counter examples which one has to bother about. So away from these counter examples, this is always true, and this is exactly the kind of counter examples which are there. So there is a paper of Patenkar and myself, which appeared probably last year in Journal of Number Theory. So finally, we could,
the motivation of
asking,
yeah.
Oh, sorry.
Yeah, so the main motivation of asking this question is to apply your result for non-CM new forms.
Non-CM new forms you can you can apply because that the group is connected. So then it does not matter.
So I mean, if we will apply your theorem for m equal to 2, probably we will get a result of Dinakar Ramakrishnan, where he has proved that
one I had covered it long back, because those things are all
no.
I had covered.
I'm saying the recent result of Dinakar Ramakrishnan in the appendix, where he has proved that the new form can be recovered by the normalized by part of the normalized eigenvalue.
Yeah, right. No, so Dinakar's result was what led me to look at it again for symmetric powers and higher X-ray powers, many other things. And then I covered some of these results in conference proceedings in Hyderabad.
Okay, I will look at it.
Yeah, so it's there in my web page. If you look at it, it's there in the right. So where you can work with symmetric powers or tensor powers, because in the non-CM case, the algebraic group is GL2, so then it's connected, and so many things go through, and it's also acting absolutely irreducible. So all those things can work, and it not only second symmetric power, it can work with any symmetric power in those cases. We can work with almost any faithful representation of GL2.
Just one last question. So when you extended this faulting results for character, so can you give an upper bound of the cardinality of T?
Of T?
T, the set T, you have said that there is just a finite.
Depends on whether you have effective versions for Hermite-Minkowski and things like that, right? Even in the original Faltings theorem, the set T I know is finite, so you need to have some effective Hermite-Minkowski and something. So I'm sure there are such results, but I don't know how good effective versions of Faltings people have been looking at. But that is that's not. I really don't know what the best results there.
Thank you.
Yeah. See, there is a slightly different question out here. Is that in the Faltings or whatever, you have to fix the residue field cardinality, right? But then there are theorems, or conjectures coming from Serre conjectures and such things, where you expect that there are only finitely many representations up to semi-simplification or pure or odd or whatever into, say, GL2 of FP bar or something, right? But so then so it's not clear how do you can you relax the restriction that residue field of F has bounded cardinality, say L power A or something. And so Serre attempts it in a paper under some conditions, that is, this is what is called, wait, I've forgotten this, sorry, I forgot there are some things. So, but he does it in some kind of residue characteristic too under some conditions. So, but it's not clear what exactly are the. It's a very it looks a very intriguing question.
Thank you.
So are there any more questions?
Rajan?
Yeah.
No, I was just wondering about this Bajij and Boxall. I did not know about this.
Yeah.
It's some theorem about elliptic curves.
Yeah, they no, okay. See, that theorem about elliptic curves is not the main goal. What the main goal is to, I didn't cover it because I didn't have the time, is see what they are trying to look at, or they want to construct algebraic curves of higher genus, which has everywhere good reduction. Okay, or a number field. What are the smallest degree number fields you can have, so that you can have, say, curve of genus 2, which has everywhere good reduction. And so what happens is, if the curve has good reduction, then the Jacobian has good reduction, but it's not the other way around. You know,
Yes.
so you have to look at some outer. It's a very interesting theorem of Takayuki Oda for giving necessary and sufficient conditions for a curve to have good reduction. Yeah. But anyway, so they are trying to do that. In that process, they came to this concept of potentially good reduction. You know, what if managed to get this produce infinitely many pairs of quadratic number field K and a curve C, which has good reduction in some quadratic etc. Everywhere good reduction. See, there are these theorems of Fontaine. You're quite right. There are no abelian varieties defined over Q and such things. So you know that there are no curves which have good reduction over Q, but other curves which are defined over a number field, quadratic field, or what is the smallest degree, quartic fields or whatever, and how many are there? Is it finitely many?
But the theorem that you quoted was some finiteness theorem about number of non-CM elliptic curves.
Yeah, right. Yeah, see that they give the proof. Yeah, that they prove it and they give a proof of it. Right?
But no, my question was whether such a theorem is true for abelian varieties by your methods.
Yeah, but as I said, provided the algebraic monodromy group is acting, connected component acts absolutely irreducibly on the thing.
But that is not given to you, so
that is not so. For such classes of abelian varieties, one can prove those results.
But there is some possibility that it goes wrong.
Yes, it can go wrong. Yeah. You can see that. Yeah, it can go wrong. But I really don't know. So that is something which we are wondering for. What do you say about potentially good reduction? And that is what we could do it at the end. For abelian varieties which have potentially good reduction by a quadratic extension, then we know that, elliptic curves which are potentially good reduction by a quadratic extension, we know that there are only finitely many.
So there is a possibility that there are infinitely many abelian varieties which are potentially good outside a finite set.
Yeah, so there is this conjectures of Hida, where he says, he does say that there are only finitely many, right?
Hida,
yeah. He does that JAMS paper of 2012. He is looking at GL2 type abelian varieties. But here, for Hida, the dimension D also changes. The dimension of the abelian variety can go off to infinity. So it is not a problem, but then he still says there should be only finitely many. But it should have ordinary reduction at the place. So you need some, he's assuming that it has some.
No, but one must fix the dimension, no?
No, but he is looking at GL2 abelian varieties. So that means the Galois representation actually lands inside some GL2 of some number field, E lambda.
But
because endomorphisms is a field of dimension G, degree G, right?
But G is not fixed.
But G is not fixed. So because the endomorphism is not, it's not commutative, he's assuming non-CM, is assuming non-CM, but assuming that the endomorphism is a field of dimension G.
Recording stopped.
Right, and then so then the Galois representation of the Tate module goes to the, it commutes with this endomorphism ring, so it goes into GL2 of this E lambdas, right? Where if E is the endomorphism field, then you complete it E at some places, EV here. So it will go into GL2 of EV. So you have a compatible family of representations. So Hida proves it for when the ground field is Q. And but there is an ordinarity assumption there. It has to have some ordinary reduction. Yeah. So this, yeah, I've been thinking, but I'm getting it. Looks very confusing and difficult. I don't know. I don't really get to understand it. It's kind of, I told you, it's related to this Ribet's Q abelian varieties. Where you can have things which the variety is defined over Q, but the components are defined over some the irreducible components are defined over some larger extensions, right? And then is there some finiteness results for such things? It's not clear how to do that.
Okay.
Yeah. So yeah, it's a bit confusing. I think I don't fully understand what is happening there, or I don't understand Hida's paper either. So,
so I mean, just to summarize, there could be infinitely many abelian varieties which have potentially good reduction outside a finite set of a given dimension.
Yeah. Yes. I don't know. Yes.
It's possible.
It's possible.
For the moment.
But
for elliptic curves, it is, because you are using non-CM, there is no possibility. That's what you have proved.
Wait. Yeah, non-CM should be, yeah, right. Wait, no, I'm not, what I proved is by quadratic extension. But say, suppose it can have a good reduction by a cubic extension, right? Then I don't have, then the inertia can act by, all we know is by this Lenstra and Oort that the inertia does not take the eigenvalue 1, but it can take eigenvalue cube roots of unity, which is not 1, even for an elliptic curve. And I don't know how to prove that.
All right. So there are many questions to be answered.
Yeah, yeah. So I don't, yeah, right. Definitely. We don't know even for elliptic curves, non-CM elliptic curves, we don't know. It would be a very nice question to answer. But I don't even know whether it is, the theorem is true or false. I think it might be false. Maybe if one tries to sit down and compute, you want it to have some potentially good reduction over some finite extension. Look at the collection of non-CM elliptic curves which have potentially good reduction outside some.
No, you are fixing a number field? No?
Yeah, fix a number field.
Yeah.
And look at the collection of ellipticals which are potentially good reduction outside some set of places, yes. Or which are potentially good reduction. That's it.
Up to isomorphism. Up to
isomorphism. Yes, everything up to isomorphism or whatever. Yeah, or isogeny, isomorphism, yeah, whatever. These are other only finitely many.
Okay, so for the
up to twisting, of course, you have to twist by some characters or something, right?
No, but that's a finite set of characters, no? You are looking at.
Yeah, right. That will be a finite set of characters because that will be, yeah, right. If you fix a dimension G, it will be finite set of characters. Yeah, right. Right. Yeah. Yeah, I don't know. It's a question. Yeah, I really don't know what. Like, just assume. Suppose the elliptic curves have. Yeah. By this Serre-Tate, that it should have the field should be of, I think, extension should be of degree 12, I suppose, because that is a kind of thing one works with. But
so sorry to interrupt, but we are running out of time.
Yeah. So thanks, Anup. Yeah.
Okay, so let us thank the speaker. Okay, sir. Can you stop sharing this screen?
Yeah, I'll do that.
Okay, sir. Thank you.
It's fine now?
Yes.
Okay.
So our next speaker, sir.
He's there. I think he can
Kalyan
start.
sir, are you there?
Yeah. Can you hear me?
Okay. Yes, sir. Can you please share us your
Yeah,
screen
let me
to
try,
check
yes.
things up?
Yeah. Is it okay?
Yeah. Mm.
I
Yes, it is fine.
Yeah.
Yeah. So we have 2 minutes, so we can wait.
Yeah, sure. Hi, Ramki.
Hi. Nice to see you.
Yeah. So it's not your birthday today, no?
This is what to say. People say that my birthday is 9th August.
Okay. So not too far
Not
behind
far,
us.
Yeah. Right.
So that's why, I mean, I was writing that, celebrating.
I know.
Yeah, celebrating, that is fine.
Yeah. I just changed it a little bit.
So how are things in Kerala?
Yeah, things, I mean, if you are asking about COVID, it's...
Yeah. That is a
it's-
whole main problem.
That's
for
the
all
only...
people.
Yeah, it has improved last couple of days, and I think now everything is open, kind of thing.
What about Nipah virus?
Sorry, Nipah.
Nipah.
Yeah, near my house there was that first death. That child died. No, near the place where I'm staying. But they have really ruled out no more. And suspected one more case in Kannur, let's say. Another girl died, young girl. So they're suspecting it is Nipah. I hope that it doesn't come.
It's almost time, so we'll just.
Oh, I think it was mute. So let me introduce our next speaker. So our next speaker is Professor Kalyan Chakravarti. He is director at KSOM, Calicut. And today he is going to talk about stump type bound for square-free coefficients of Hilbert modular forms. So before we start this, I would like to ask permission to record this lecture and stream it on YouTube.
Sure.
Okay, thank you, sir. So now I request you to start your talk.
Yeah, so firstly, I would like to thank the organizers. I was just thinking that, when we are going to organize this kind of felicitation for Professor Ramakrishnan, and, you showed the way, and I am sure that a couple of more are going to come up very soon. And so I thank the organizers for really, firstly, to organize such a conference in the honor of, Professor Ramki, as he popularly is known, and for giving me a chance to really speak here. And I immediately grabbed it once I got the invitation. So let me tell a little bit about, Ramki, as people are all serious mathematics is going on. So I am the first student of Ramki. And, it was almost, if we are not too far as age is concerned. And so it's like a friendly relationship that I had with Ramki. And I got I was privileged to have the only student. And in fact, all the time of Professor Ramakrishnan, learned everything from him. And he taught me even how to write, how to take and how to write a paper. And, I used to go back after discussion. We were staying together. and he will cook. And this famous pongal and dosa and idli, and really had a great time with Professor Ramakrishnan. And I'm sure that at this milestone of his life, he must be looking back and proud. You should feel. I mean, I'm sure that you must be feeling proud looking at the students that you have. Students are all, I can see all of them are here, most of them, and they are all placed in very good places. And the way you have brought them up academically, in every way. So that's real credit to Ramki. And he's so caring. That's one part that I have learned, at least. I am sure all of his students have learned that part from him, to take care of the students. He's one person to whom anyone can go at HRI over the years. And now I'm sure he has taken up a new responsibility. The place also will come up similarly. So I chose this topic to really symbolize, in the sense that I'm the first student, and it's a joint work with the youngest student, which Ramki, who will be submitting thesis very soon, Rishabh Agnihotri. In some sense, it's a good symbol that the first one, and I don't know the last one or not, but Ramki might take more students, but with Rishabh. So yeah, I really wish, pray my prayer, my best wishes for Ramki to carry on like this for long years to come. He has to contribute there. With these few words, let me go ahead with my presentation.
Okay, thank you.
So the title is quite well known. It's the Modular Form Conference in Modular Form, the Stram bound for square free coefficients of Hilbert modular form. So as some introduction, then I'll talk about the main theorem, some tools, and some idea of the theorem, and then end with some references. So modular forms, that's nothing there to really introduce, but just to keep the notations going. K and N are positive integers, gamma naught n, all of us know. And the definition of modular form, just to put it on the frame, all of us know. And it's a cusp form if it vanishes at all the cusps. And in particular, we have this nice Fourier expansion for these objects. And these AFNs are called the Fourier coefficient. And in particular, AFN will be the NS.
Sorry to interrupt, sir. Rashi, recording is not on, I think.
No, the media team is recording it. It's fine.
Okay, fine.
Yeah.
Sorry,
okay?
Yeah.
Yes.
Yeah. Yes, so AFN will be denoting the NS Fourier coefficient for this form F. And we have MKN and SKN as usual. So a classical question in this theory is to determine a modular form. I'll more specifically will tell what you mean by determination of a modular form by a subset of all these Fourier coefficients. So in this direction, the most talked about result is the so-called, that is the title, the Stram's bound, which states that you have a positive constant lambda, such that you have to count only that many, like lambda k is the weight, and n is of course we have fixed. So if AFN is 0 for all these n's up to that lambda kn, then in fact the form is identically 0. Okay, so in other words, suppose you have you can transform or translate this question to this question, that I have two forms given, F and G, two cusp forms. And if we can compare the coefficients Fn and J, and you see that they're equal up to this bound lambda kn, then we conclude that the forms are identical. It's the same question. So there are many results, such Stram type of results, like one can talk about multiplicity 1 theorem, which states that if two new forms have the same eigenvalues for almost all the, Hecke operators TPs, then these forms are identical, almost all. And a stronger result we have of, which is of Dinakar Ramakrishnan's, that one has to check the primes, only that set of primes having the Dirichlet density more than 7/8. So these are some results which are there. There are many more results. So just some of these results which are interesting in the literature. So a similar question one can ask that, we are adding over all the Fourier coefficients n. Now you confine yourself to square free Fourier coefficients. Okay, and a variant of this question will be how many square free Fourier coefficients are required to determine a modular form, determine in that sense. So for classical modular forms, the answer to this question was given by Anambi and Somo. The first one of their work, they used prime number theorem for L function associated to these primitive cast forms, and obtained an upper bound, which was in fact exponential, the first result in nature. Later, they improved the bound by using the Rankine-Selberg L functions for primitive cast forms. And their result is this. So chi is a Dirichlet character modulo n with conductor m chi, such that n over m chi is square free. And let f in sk n chi, certainly non-zero we are taking, and fix an epsilon bigger than 0. Then there exists a square free integer n, square free, less k to the power 3 plus epsilon n to the power 7 over 2 plus epsilon. This is the bound they got from the exponential one from there to here, such that if AFN is non-zero up to this, AFN is non-zero. So that means the form is non-zero. You have to check only that much. If you find that you find one AFN which is non-zero, then the form is in fact non-zero. And this implied, this constant here depends only on this epsilon that you have chosen. Okay, so this is the classical result by Das and Anambi. So the purpose here in this talk is to consider the same question for Hilbert modular forms, general Hilbert modular form. Let us go into a little bit of this Hilbert modular form, and we will be using this adelic setting. So just a little bit about that before we go into the theorem. So F is a totally real field. All the embeddings are real, and degree is n, number field. And I'll be denoting by OF the ring of integers, and H by narrow class number of F. By narrow class number, I mean the order of the narrow class group, and narrow class group is simply, IF. Take all the fractional ideals and quotient it out with principal fractional ideals generated by totally positive elements, generated by alpha, so that sigma of alpha is strictly bigger than 0. So that's what is called narrow class number, the order of this group, narrow class group. And choose a complete set of representatives of this narrow class group. Let's call it Ti. And this collection I equal to 1 to H. H is the order of the narrow class group. Now, corresponding to each integral ideal, let's call it N, I mean that Gothic N. And each representative for this Ti, what we have it here, for each of these representatives, there exists a congruent subgroup that's of GL2F. Let's call it gamma IN sub I. I will be symbolizing that representative, ith representative that we have chosen. So this is simply gamma IN is AD, where A and D will be coming from the ring of integers. And Ti is that representative, Ti inverse, B, TIC, and B is in the inverse of the different ideal. These are invariants associated with the field F, and C is n times that different ideal, belongs to that. Okay, and AD minus BC is a unit. So this is gamma IN. So each of these representatives, if I choose, I will have a congruent subgroup gamma IN of GL2F described by this. Now you have to fix some multi-index notations, because we'll be in Hilbert modular form. So K for me is K1, K2, Kn, positive integers, and not putting any condition, no parallel, nothing. So they could be all distinct. And Z is Z1, Z2, Zn. And for any scalar A, Zk will be this multi-index notation. Z to the power k, Zi to the power kj, j equals to 1 to n, and gamma k will be similarly, and k naught for me will be the max of k1, k2 up to kn. This will be fixed throughout. And a to the power k is simply a to the power sigma j equals to 1 to n kj for this multi-index notation.